Hello guys, in today's video we're going to see some very interesting theorems related to reflexivity, and let's start with this lemma. So I have X, which is a reflexive Banach space, and Y a closed subspace of X. So if X is a reflexive Banach space and Y is a closed subspace of X, then Y is reflexive. It's not given. So yeah, that's the goal, and we start as follows. So what we do is, so this is a very technical proof. There are like so many things there, so let's break it down into chunks. So what we do is we first see where each of our element lies. So I know that X is a reflexive Banach space, so this identity mapping, this I, which is my linear isometry, which I saw in the previous video, is surjective. So I from X to X star star and J from Y to Y star be the canonical embedding. So as of now, I just know that they are canonical embeddings. And next, I know that I is surjective and would like to show that J is surjective. Because if this J is surjective, this canonical embedding, that is J of, well, J of Y is equals to some F. I know that I is surjective and I want to show that J is surjective. So by surjectivity, I mean that take a F in Y star star and find me a Y belonging to Y such that J of Y equals to F. So when this is done, then I can say that this J is surjective, and when this J is surjective, then my space Y is also reflexive, because this J of, like in the case before, I had the equation of linear isometry, which used to go like this: I of X of t is equals to T of X. Now I just want to take that J of, say, Y, say, of S is equals to S of Y. So if this is the case, then if this is the case for the linear isometry, or the canonical embedding as I call it, and if this canonical embedding is surjective, then I say that my space Y is also reflexive, and that is my goal in this lemma. This, I take a F in Y star star and I will find me a Y belonging to capital Y such that G of Y equals to F. So let's get started. So now choose, in my space X star there is a point T, okay, and in my space Y star star there is F, and my space Y star there is a point T restricted to Y. So the way I can define a point like this is with the help of Hahn-Banach theorem, that operators, functionals can be extended with the unique norm preserving property. So I can define this T and T restricted to Y in that sense of the Hahn-Banach. I can use consequences of my Hahn-Banach to describe relationships between functionals in this way. So now what I say is that I need to construct a G of F such that this G of F is defined with this formula. So why we are doing so would be made clear as we go further. So just look at this. So this G of F is given like this: G of F of t equals to F of t restricted to Y. So I know that F belongs to Y star star. I know that t restricted to Y belongs to Y star. And now I'm constructing a GF, and I want to show that this G of F lies in X star star. Okay, so if you look here, you see that choose F belongs to Y star star. I have an F in Y star star, and I'm defining this G of F with this formula, and I want to show that this G of F lies in x star star. So the way I do is if I want to prove that g of f lies in x star star, which is the space of all bounded linear functionals on x star, then I want to show that this g is linear, which can be shown like this. So, well, if g of f is given by this formula, then if I just replace t instead of t1 plus t2, it looks like this. And I know already that this f belongs to y star star, which is the space of all bounded linear functionals on y star, and t1 restricted to y and t2 restricted to y are elements of y star. So I know that, okay, since this is a bounded linear functional on y star, this can be split and written like this, but these individual elements are themselves equal to g of f of t1 plus g of f of t2, and hence this is linear in t. And the next thing is I have to show that this g of f of t is indeed bounded. So this is a very simple argument. I just write down the formulas and then I use Cauchy-Schwarz. That's all of it. So norm of f lies in y star star, norm of t restricted to y lies in y star, but if t lies in y star, then t lies in x star. So I can write it like this also, since y star is a subspace of x star. So now I showed what have I done now? I have constructed a G and show that this G of f belongs to x star star. This is what I have done. How I have shown that G of x belongs to x star star? By showing that G of f is linear and bounded. So this was step number 1. Now stay on the diagram, we would need it. Now I say that there exists a x belong to capital X such that I of x is equals to G of f. Why can I say that? Because I know that x is reflexive, which means that I of x is equals to G of f. So it simply means that given a G of f, I can find x belong to capital X such that I of x equals to G of f. The basic or the usual surjectivity argument that we always use. Now, I know that if I apply t on both the sides of I of x and G of f, it looks like this. And the next thing that I do is that instead of I of x of t, I write it as t of x. And instead of G of f of t, I write it as f of ty. So I get this formula. Now, this formula is valid for all t belonging to x star. So that's what I'm focusing on, that for all t belong to x star. Now I have shown, this is like my step 2, this. So yeah, the summary argument of step 2 is, since I was surjective, I found some x belonging to capital X such that I of x equals to G of f. And in step 3, what I do is I claim that this x that I chose belongs to y. And how I show that? Now, if you look at this here, it says that t of x equals to f of t of y for all t belonging to x star. And suppose if I take a x here, which is, now this space can be written as x complement y, this whole space is x, and y is a subset of x. Now, if I have this case, if x belongs here and x complement y, then I know that there exists a t tilde belonging to x star such that t tilde puts everything in y to 0 and t of x is not equals to 0. So if this is the case, if x belonging to, so if you look at this diagram, x either belongs here or here, it's x is a Banach space, y is a closed subspace of a Banach space. So x can either lie here or x can lie here. Now if x lies here, then there exists some t tilde such that t tilde of x is not is equals to 0, but on the right hand side, f of t tilde restricted to y would have been 0, because t tilde is an annihilator of y. So everything, if you feed anything in t tilde which is an element of y, it annihilates it, means it maps it to the 0 element. So this would be 0, and t tilde of x would not be equals to 0. So otherwise there exists a t tilde belonging to x star, with t tilde annihilates everything in y, and t of x not equals to 0, which contradicts this statement, because this is for all t belonging to x star. But yet, if x is in x complement to y, then it is not true for all t belonging to x star, because I just used a corollary from the Hahn-Banach theorem that says that, let me show you that to you once. Let x be a norm space, y a proper closed subspace of x, and x belongs to x complement y. And it says that there exists a t which is an annihilator of y with t of x not equals to 0. So thus I'm explaining this case, just this line from this. So all it is saying that, okay, my x must belongs to y, because if it does not, if it belongs here, then it is not true for all t belonging to x star, this equation. And in step 4 now, what I show that, if you remember what I originally wanted to show, I wanted to show that j of y, I wanted to show something like this, that j of y is equals to f, where f belongs to y star star and y belongs to capital Y. And now I have to show in step 4 that j of x is f. So till now I have shown that x belongs to y and f was an element in y star star. Now how would I show that? Now choose s belongs to y star. So if you just look at this diagram again, I choose a s belonging to y star, and let t belonging to x star be the norm preserving extension of s. So yeah, of course I can do that because of Hahn-Banach theorem. Bounded linear functionals have a unique norm preserving extensions. I've seen these kind of things in Hahn-Banach theorem. So yeah, I saw that bounded linear functionals have unique norm preserving extensions in complex spaces, in complex norm spaces, in real vector spaces, and thus my operator or my functional s in y star has a unique norm preserving extension t belonging to x star, and it implies that Now it implies that S of x is equals to f of s. Now why have it implies that? Now the thing is that if you look at the diagram again, so S of x, so now I have shown that indeed x is an element of capital Y. So S of x is equals to j of x of s. Why? Because j was a canonical embedding, and I know that if t is restricted to y, it is given as s. So just using this equation, I can write j of s, j, or sorry, I can write, so rather than t of x, I can write s of x and f t of y. So t of y is again s. So I can, using this definition, I can simply write this because t restricted to y exactly is s, and rather than writing t of x, I can use s of x when my x belongs to y, because t is a non-preserving extension of s. So I get this formula, and from this formula I know that, okay, s of x equals to g of x of s here is equals to f. And this is exactly what I wanted from step number one. From that was what my goal was. If you see that, take f belonging to y star star, find me a y belonging to capital Y such that g of y equals to f, and I did find you a y, and that y in this case is x, such that g of x equals to f. For each f in y star star, that's important, for each f in y star star, and therefore there exists an element x belongs to capital Y with j of x equals to f, and f is surjective. So that was a pretty intense proof. Is a non-preserving extension of S. So I get this formula, and from this formula I know that, okay, S of x equals to g of x of s. So I can then say that this j of x here is equals to f. And this is exactly what I wanted from step number one. From that was what my goal was. If you see that, take f belonging to y star star, find me a y belonging to capital Y such that g of y equals to f, and I did find you a y, and that y in this case is x, such that g of x equals to f. For each f in y star star, that's important, for each f in y star star, and therefore there exists an element x belongs to capital Y with g of x equals to f, and f is surjective. So that was a pretty intense proof.